We started the recording. This is the first class of the Radioactivity chapter, nuclear physics for the A2 syllabus 9702. There are a couple of things which are quite new. Actually, Radioactivity is one of those unique chapters which we have learned throughout our syllabus in the CAE syllabus. We had it in O levels, we had a little bit of it in the AS level, and it is continued on to the A2 level as well. Few other chapters are like that it didn't show up in the AS, or then it didn't show up on A2. For example, thermal did not show up in AS. Now it's popping up in A2, and so once again, waves showed up on AS but not available in A2 anymore. Magnetism was in O levels but not in AS but in A2, something like that. Basic electricity was in AS but not in A2. But electricity is required everywhere. I mean, the Ohm's law is a thing that you will be always needing, like in almost every case. Anyway, so let's start, and with this paper, I can use this as a guide, and I'll also discuss multiple things with you. First variable that we're defining in this note is what we mean by decay rate or activity. The word rate itself means that it is something that is with respect to time. So number of radioactive nuclei decayed in 1 second is activity at that moment of that specimen. At that moment part is important because radioactive decay is a continuous, natural, spontaneous process. So if you allow a certain radioactive specimen to decay over time, as more time goes by for that same exact specimen, its radioactivity will slowly go down. Which means if you start at t equals to 0 after at 1 hour, 2 hour or mark, or 2 days, 3 days after, you should not expect the exact same activity. The activity will reduce because the number of available nuclei which can undergo nuclear breakdown, that will become less because they have already undergone breakdown. More massive unstable isotope and / or more radioactive isotope who gives more activity. So more massive means just bigger in mass. So if you have more unstable nuclei, or if you have more massive of less unstable nuclei, both of these factors individually or simultaneously can increase the activity of a specimen. For example, if you consider the activity for uranium-235 nucleus isotope, that is quite higher compared to uranium-238. So if you have equal masses of two isotopes, one from 235, one from 238, obviously the uranium-235 will give you higher activity. Every single second it will undergo increased number of breakdown, and so on and so forth. Activity is given in numerical terms as minus dm by dt. We give a minus sign because this is the number of nuclei that is decreased. So it's an induction process. That's why we give this minus sign. This minus sign will also become handy for the equation after a while. Now, here comes the information. Absorb this information. Activity is proportional to the number of undecayed nuclei at any given time. Which this is supposed to be proportional design. This is a bit upside down. I mean, horizontally flipped. It's supposed to be proportional. So consider this to be a proportional sign. This means that if in any specimen, the number of undecayed nuclei that you have at any instant is directly proportional to the activity of that moment. The fewer the number of undecayed nuclei, the less is the activity. So it is given by this proportionality that A is directly proportional to N, where N is labeled as the available number of undecayed nuclei at that instant in that specimen. And just to make this into an equation, we can bring about a proportionality constant, which is labeled as decay constant. This decay constant is apparently looking like a tau, but it is not supposed to be tau, it's supposed to be lambda. Maybe it was my bad handwriting, or maybe it's the students' handwriting. Irrespective, I take blame because I'm using this material. This is supposed to be lambda. So A goes to lambda n. Lambda is the decay constant. Decay constant for a specific isotope is a fixed number. It is somewhat similar to like density or specific capacity. For a fixed isotope, the decay constant is a fixed number. For example, uranium-235 isotope has a decay constant. No matter how big of a lump or no matter how small of a lump you take, you will always have that decay constant. It is a property of the material of the isotope.
স্যার এটা কি ডেটা বুকলেটে দাও থাকবে ল্যাম্ডার ভ্যালুটা
বলতেছি এটার ক্যালকুলেশন পরে আসছে বলতেছি এটা কোন জায়গাতে লাগবে. It has different value for different isotopes, so you cannot have the value for all the isotopes given into it. This is not an universal constant like Planck's constant. This is a material or isotope based constant. Like density of different element is different. Similarly, decay constant for different isotopes are different. So you are not going to have that exact value. No value of this thing would be available to you in the data booklet. Uh, but there are ways to calculate this value with other variables, which is going to pop up in the later part of the lecture. Yes, Shubho?
স্যার বলছিলাম যে ক্যাপিটাল এনটা কি আসলে মানে নাম্বার অফ নিউক্লিয়াস নাকি নাম্বার অফ আনডিকেড নিউক্লিয়াস এক্স্যাক্টলি?
Number of undecayed nuclei.
আচ্ছা
Then if you subject the
Sir.
from this equation, we get lambda equals to a divided by n. So this is the subjected form. And from this equation, we define the lambda. If n equals to 1, that is, if one atom remains, then lambda equals to a. So from this thing, we define that the decay constant is the mathematical probability for each nuclei to break in unit time. So this is the definition for decay constant. It is the mathematical probability for each nucleus, each nucleus that plural হবে না, for each nucleus to break in unit time. Unit time মানে হচ্ছে every second. So decay constant essentially comes in terms of per second. Per second এর একটা SI একটা ইউজফুল কনভার্সন হচ্ছে হার্টজ, যেটা আমরা ভাইব্রেশন চ্যাপ্টারে পড়ি বা অসিলেশন চ্যাপ্টারে পড়ি, সাউন্ড টাউন্ড এগুলোতে আছে। For radioactive decay process, the decay constant is practically used as per second, second inverse 1. But in terms of radioactivity, sometimes this unit is also named as becquerel. Becquerel is named after the scientist of Henry Becquerel. His name is spelled by Becquerel, Becquerel, but to write it in short form, we sometimes write BQ. So if I mention that the decay constant of, let's say, isotope X is, let's say, 2.3 BQ, it means its decay constant is 2.3 second inverse 1 per second. হ্যাঁ, ফাইন বলো।
স্যার এখানে h equals to মাইনাস কেন সামনে, ওই যে dn by dt, ওই যে ডিফারেন্সিয়েশনের ওই এক্সপ্রেশনটা?
Because the breakdown is a negative process. Over the time, your number of nuclei is going to decrease. So if you calculate the amount of change over the duration of time, final minus initial always gives you a negative value.
আচ্ছা স্যার, ঠিক আছে, থ্যাংক ইউ।
Sure. Then comes the mathematical part, that if we have a radioactivity equation, so a equals to lambda n, so minus dn by dt equals to lambda n. From here we take the similar variables on the same side, so dn by n equals to lambda dt. So now we're going to integrate this equation, and for integration we're going to apply some limits. Try to understand these limits over here. The n is integrated from a range of n naught to n. N naught is the initial number of undecayed nuclei, which is available at t equals to 0 second. Initial means at the beginning of the observation, t equals to 0. And n, capital N, only n, is the remaining number of the undecayed nuclei at t equals to t second, or t equals to t time. So we are integrating the time from t equals to 0 to t equals to t. Within this time, the nuclei number reduced from n naught to n. So n always represents the number of undecayed nuclei. N naught represents the undecayed nuclei number at the initial stage, or at t equals to 0 at the start of the observation, and n represents the number of remaining undecayed nuclei after a duration of t time. So whenever we do this whole integration, we have ln and everything, and it shows up blah blah blah. You can look up this equation. There is a minus sign because of the minus, and then we have n by n naught equals to 0 minus lambda t, and ultimately this is the whole equation, which is given by n equals to n naught e to the power minus lambda t. This is the primary decay equation, radioactive decay equation, that we're going to use for our discussion throughout the chapter. However, this equation can also be converted into another form, that because A is proportional to n, I mean activity was defined as a proportional to the number of nuclei available at any instant. So this equation can also be written in the form of activity, which means we can write this equation. If we want to write in terms of activity, this can look like activity equals to current activity equals to initial activity into e to the power minus lambda t. And also, because the number of nuclei by the ratio of Avogadro's constant, the number of nuclei can also respond to the mass of the isotope piece or isotope lump. So mass is directly proportional to n. A mass is directly proportional to n is relevant to the mole number constant or molar constant, Avogadro's constant, something like that. So if we have bigger number of radioactive nuclei, the mass of the lump is supposed to be bigger, and so on and so forth. So we can also write that m equals to m naught e to the power minus lambda t. Now, one thing is really important for you to understand, that this mass proportion is exclusively dealing with the mass of that isotope. It is not the mass of the isotope lump altogether. এখানে lump কথা actually না থাকলে ভালো হতো. I might as well cross this out right now before I go ahead and printing, and you have this with this word.
স্যার লাভটা কি মানে?
Lamp na lump মানে টুকরা, piece.
ও আচ্ছা আচ্ছা।
This should not be here. It's about. So why am I crossing this out? Why am I crossing this out? Let me explain why am I crossing this out. Because you have to understand one thing. Let's say in a certain let's say a certain relative specimen is just purified. Let's say at initial stage you have 100% X in that material. Let me write this so that it can make better sense maybe. So let's say in a relative specimen currently we have 100% X isotope, 100% X. If the half-life of this relative isotope is, let's say, 1 day, half-life is represented by T half, or sometimes also represented by tau. For reasons unknown, they use tau. It means after 1 day, the remaining isotope, this lump would have 50% X. After 2 days, it will have 25% X of the initial mass. Then it is going to have 2.5%. And this process is going to keep on happening after every day. Does this mean that if this block had a mass of, let's say, 100 gram, this block would have a mass of 50 gram? Does this mean that? This is my question. Or subsequently, this block would have a mass of 25 gram. Would it mean this? Would the mass of the whole block reduce by a factor of 2? I'm asking you kids. Someone tell me.
কোশ্চেনটা একটু রিপিট করেন।
The concentration of the relative isotope X is gonna reduce by half every day, because I have defined that this X isotope has a half-life of exactly 1 day. So if this initial mass of this whole isotope of 100 gram X at on 0 day it was 100 gram, would its mass after 1 day will become 50 gram, and after another day it will become 25 gram? Is it gonna change like that?
Yes.
ইয়েস স্যার, সেটাই তো হওয়ার কথা।
Okay, let me ask you this question then. Whenever reactive decay happens, natural radioactivity, does the entire atom convert into energy? Does the entire atom perishes altogether?
নো 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 নো,
Let's say
কিছু
you
তো
have-
স্যার থেকেই যাবে।
let's say you have a certain radioactive specimen. It undergoes some sort of radioactivity, alpha decay or beta decay. Gamma radiation is associated with both of them anyway. So let's say alpha decay, beta decay. Any of them happen, or maybe both of them happens. Does the entire atom, including its nucleus and electrons and everything, does it altogether vanishes up, or it just converts into something else? What happens actually?
It converts into another element.
It converts into another element. Its mass is going to reduce by a small amount because it will be emitting out those ionizing radiation. So it might be emitting quite a good number of alpha particles, quite a good number of electrons. Some gamma radiations will be coming out, which comes from the mass deficit, which you're going to see after a while. Don't worry about that. So its mass will decrease, but it does not become half, because the entire atom of X does not just go vanish. It simply converts into something else. So if it so happens that in the process of this conversion, let's say if the relative decay of this element isotope is, let's say, X converts into Y, emitting an alpha particle, this would essentially mean that after 1 day this will be 50% Y plus 50% X. After another day, after 2 days from the beginning, it will be 75% Y plus 25% X. I'm showing the concentration over here. After another day, this will be 87.5% Y and 2.5% X. The concentration of X is going to go down and the concentration of Y is going to go up, and it's going to emit some alpha particles in that process. The total mass of the block would be almost as equal as 100 grams throughout the process, almost same, because the mass of alpha particle is actually very small. It would not be exactly the same. Obviously, we can calculate out how much mass this is going to lose, provided all the alpha particles are actually emitted out into the out of the block. If none of the alpha particles got absorber got stopped by that block within the block. If that did not happen, for the sake of argument, the mass of the block would reduce by a small amount. And how much would be the mass of the block? For example, if in this process we had, let's say, 1 million alpha particle shot, the actual mass of the block would be 100 gram minus 1 million into mass of one helium nucleus. So you're gonna have that much shot. And then on the next day, you're gonna have half of that shot. On the next day, you're gonna get half of that shot. So your mass of the block is gonna reduce, but it's simply not gonna become half of the initial value. Don't make that mistake. It converts into something else. It simply does not vanishes, or it simply does not perish. The whole thing does not convert into energy. It converts into a secondary material. So its concentration become half, but the whole mass of the block does not become half. Sometimes kids mess up this idea. I want you kids to be careful about this thing. So this equation over here is essentially showing the exclusive mass of that isotope, not the whole mass of the lump. So if you start with 100 gram mass, then after one half-life, in that block, you'll have 50 gram of that material remaining, which means the other 50 gram would have converted into something else. The other 50 gram would not simply have vanished. So that's not going to happen. Yes, Fahim, go ahead.
স্যার ওই যে অ্যালফা পার্টিকেল নিয়ে কি বললেন ওই যে ম্যাস যে কমে
যে
ওই
কটা
যে
ব্লক থেকে আমাদের যে কটা আলফা পার্টিকেল বের হয়ে যাবে, টোটাল ব্লকের ম্যাস অতগুলো আলফা পার্টিকেলের ম্যাস ইকুইভ্যালেন্ট কমে যাবে। এখন মনে করো হচ্ছে ফার্স্ট একদিনে যদি 1 মিলিয়ন আলফা পার্টিকেল বের হয়, তাহলে সেকেন্ড ডেতে 0.5 মিলিয়ন আলফা পার্টিকেল বের হবে, because your activity will also reduce as the number of remaining expo portion reduces. So একদিন পরে আমার remaining mass হবে হচ্ছে let's say 100 gram minus 1 million into mass of one alpha particle. এইটা হিসাব করলে যা আসে, একদিন পরে আমাদের ব্লকের ম্যাস হবে এটা। যদি একদিনে টোটাল 1 মিলিয়ন আলফা পার্টিকেল বের হয়ে যায়, তাহলে আলফা পার্টিকেলের ম্যাস তো কমে যাবে, মানে আলফা পার্টিকেল ম্যাস নিয়ে চলে যাবে। সো ওইটুকু রিডাকশন হবে, বাট ইট উইল নট বিকাম এক্স্যাক্টলি হাফ। দ্যাটস হোয়াট আই মেন্ট।
ওকে স্যার, থ্যাংক ইউ।
Sure. There is a way we can calculate these numbers. The relevant constants, required constants would be given to you in the formula sheet. কোন কোন কনস্ট্যান্ট ফর্মুলা sheet থাকবে না থাকবে সেগুলো আমি ম্যাথস করার সময় দেখাবো, don't worry about this. So I want you to understand that this equation is not applicable for the whole lump. This equation is applicable for the remaining mass of that isotope in that block. So all of these equations are negative experimental equation. This is supposed to be exponential equation. So might as well correct this. What is this? I cannot. Okay. This one should be, where is the text box? Negative exponential. Text box size ছোট করা যায় না? What is this? ছোট করা অপশন আসছিল। আচ্ছা, কিছু করা যাচ্ছে না। So all of these equations are negative exponential equations, so that graph becomes asymptotic with the x-axis, horizontal axis over the time. So if you plot activity versus time, or mass versus mass of that isotope over time, or number of remaining nuclei over time, we're always gonna get a negative exponential equation, which is basically the half-life equation that you have read over your O-level syllabus and so on and so forth. The next thing that we have is half-life. Half-life is pretty interesting. We have only known this from all levels. The amount of time in which the initial number of nuclei or initial mass or initial activity reduces to half of its actual value. এখানে actual না লিখে আমরা initial value লিখলে ভালো হতো। Well, already আমরা এখানে initial একবার লিখছি, so দুইবার না লিখলেও সমস্যা নাই। The idea is that the amount of time it requires for a certain isotope for its number of undecayed nuclei or number of its mass, its own mass, or the activity to reduce to half to initial value is defined as the half-life of that isotope. So within the duration of the half-life, the n will become n naught by 2. So if you start with n naught number of initial undecayed nuclei. After the half-life, you will have remaining half of that. So n equals to n naught happen in a half-life duration of time, which is tau. So this is the symbol as tau as per the student's handwriting. So here comes a bit of a calculation. Have a look. N equals to n naught by 2. এখন আমরা এই কোশ্চেনে আমরা এই জিনিসটাকে সেখানে অ্যাকচুয়ালি কিছুটা গর্ব করছে স্টুডেন্ট, এখানে সে কিছুটা লিখে নাই। আচ্ছা, I'm gonna write this for you, don't worry. So what that equation conversion is about, it can be shown something like this, is that initially we have, so original equation is n equals to n naught e to the power minus lambda t. This is the generic equation. So if you want to replace t by tau, this one becomes n naught by 2. So when the half the mass is remaining, so we have n naught e to the power minus lambda into tau. So now the t has been replaced by tau, symbol for the half-life. So if we get rid of these two parts, we get half equals to e to the power minus lambda t. Half means 2 inverse 1. So we can simply write 2 equals to e to the power minus lambda e to the minus হবে না, e to the power lambda t. t তো না, tau হবে এটা, সরি ভুল লিখতেছি। half-life presence, এখান থেকে যদি ln নেই both side, I'm going to write ln 2 equals to lambda into tau. So এখান থেকে আমরা দুটো ইকুয়েশন লিখতে পারি। একটা হচ্ছে you can write that lambda can be given by tau divided by ln 2, or in other terms I can write that tau equals to ln 2 ভুল করতেছি
স্যার
কেন?
প্রথমটা ln 2 by
হ্যাঁ ভুল লিখছি, কারেক্ট করতেছি, মাই ব্যাড। এটা হবে হচ্ছে ln 2 by tau, ln 2 divided by tau, or tau can be represented as ln 2 divided by lambda. So আমরা দুটো ইকুয়েশনই পাই, দুটো ইকুয়েশনই ভাইস ভার্সা আমাদের ম্যাথমেটিক্যাল পারপাসের জন্য কাজে লাগে। So basic idea হচ্ছে that ln 2 is the numerator for both the equation, and whatever you subject, the other thing goes at the denominator. That's how I used to remember that. So এই ইকুয়েশন থেকে আমরা হাফ লাইফ থেকে ডিকে কনস্ট্যান্ট বের করতে পারবো। সো এইটা একটা খুব দরকারি ইকুয়েশন আমাদের ম্যাথমেটিক্যাল প্রসিডিউরের জন্য, বিকজ ইন most of the question that we are going to work for regarding this using this equation, the question would not directly give us the lambda value, or the decay constant would not be directly provided to us. Rather, the question will give us its half life in its convenient preferable. For example, let's say the question says that the half life of a certain specimen is 12,000 years. ঠিক আছে, and এটা নিয়ে তো ম্যাথস করা লাগবে। সো এটাই ডিকে কনস্ট্যান্ট করতে হবে, pretty simple. You simply write the decay constant equals to ln 2 divided by 12,000 years. Now you have to convert 12,000 years into second. How do you do that? Pretty simple. 12,000 into 365 into 24 into 60 into 60.
স্যার ওই সাইনটা আসলে কি, মানে সাইনটাকে কি বলে আসলে স্যার?
কোন সাইনটাকে?
ওই যে স্যার মানে ইকুয়ালস টু ln 2 দিয়ে লিখলেন না লাস্টে, মানে প্রথমের সাইনটা কি?
এটার নাম
মানে
ল্যাম্ডা,
ডিকে কনস্ট্যান্টের অন্য কোনো? আচ্ছা,
আর এটার নাম হচ্ছে টাউ।
ওইটা আমি ভুলে গেছিলাম।
So that's how you can convert the half-life information into the decay constant information. Then you can use the decay constant information to your equation further down the line to do other relevant calculations of the math. So this is the what I'm showing over here is that this is one way that the examiners set their questions, not to give you the lambda directly, but they typically give the half-life value, and from the half-life value we can very conveniently calculate the decay constant and eventually go with our calculation. The next topic, which is very important and interesting, is what is about loss mass or nuclear binding energy. There are certain calculations which I still stutter at for this topic, and I have to take a lot of reference and reading to correct up. This happens in every batch till date. For some reason, my head is unwilling to remember this for a proper time. So এটার কিছু ক্যালকুলেশন আছে যেগুলো করার সময় আমার ভুল হতে পারে, আমি আগে থেকে বলে রাখতেছি, but eventually I can get to the proper calculation. I just have to read the whole stuff from 2 or 3 different books once again. But I know what happens over here, so I'll be telling all these stuffs in general. The idea for loss mass or nuclear binding energy goes like this. What the scientists calculated, the mass of different nuclei What they found out that the combined mass of a made nucleus is somewhat smaller than the mathematical sum of all the protons and neutrons together. So on the example that I've shown over here is that if we can somehow measure by experimentally the exact mass of a helium nucleus, which means it is a merged form of two protons and two neutrons merged, they are joined together, binded together. If we can measure the mass of a helium nucleus, this mass happens to be slightly smaller compared to the mathematical addition of the mass of two protons and two neutrons. So this amount of mass that is apparently not present in the helium nucleus is what we call the mass deficit. And interesting enough, this mass actually does exist in the nucleus, but not in mass form. This mass
Energy form.
converts itself into energy form, and this is the energy that mathematically is the required energy to combine those particles into a single structure. If I give you a bit of an idea, is that in the helium nucleus, we try to visualize. Let's say there are two neutrons and there are two protons. Neutrons don't have any charge, so there is no problem binding them. But having two protons combined within the radius range of a helium nucleus, it means that we have to overcome a significantly huge amount of electrostatic repulsion, and by overcoming that repulsion force, we have to bring up those two protons close to each other and join them together in such a way so that they would not break out from that structure. So if you try to visualize, let's say we have four particles, two neutrons and two protons in four different sides of infinite distances around you. And now you're going to bring those particles from infinite distances and merge those four particles into one single nucleus. Now, to bring the neutrons closer, you don't essentially have to do any work. If you think that, sorry, there will be some relevant for gravitational work, the answer is correct. Gravitational work would be done by these particles. This can be also calculated, but for the time being, I'm not taking that part as a significant portion of the energy, because what we have shown in our electrostatic chapter, that electrostatic force, Coulomb force, is actually way too much stronger compared to gravitational force. So the amount of work done that will be provided by bringing those particles close to each other by gravitational force is too small compared to the amount of work that we actually have to do to overcome the repulsive force between the two protons, to bring them from infinite distances and eventually merge them into a single nucleus structure. So if we keep on doing that, we have to do some work. And let's say we do this and eventually we combine the whole thing into a single helium nucleus. The amount of work that we would have to do happens to be the amount of energy that is going to be stored within that nucleus as work done. And that energy is essentially comes from that mass deficit. What it means is that it shows up over here is that the difference in mass is called the mass deficit. This lost mass is actually converted in energy following E equals to del times C squared. Del time in this case means the difference of these two sides of this inequality. So this is the amount of lost mass, and is responsible to keep nucleus bound together, overcoming the huge repulsive forces among protons. This energy is named binding energy. So the energy that binds the nucleons together, protons and neutrons within the nucleus, that energy is called the binding energy. Some is also called nuclear binding energy, nuclear binding energy, pretty much the same thing. And if we divide the binding energy of the nucleus altogether, divided by the number of nucleus, we get BEP. আচ্ছা এটা actually student এই পার্টটা উপরে লিখে ফেলছে, this should be over here. So binding energy of nucleus, this should be the numerator, divided by number of nucleons, it means the total number of protons and neutrons in nucleus. This ratio is named binding energy per nucleon. So this is also another important quantity for a different isotopes. So we can talk about this quantity.
স্যার আপনি বাইন্ডিং এনার্জি অফ নিউক্লিয়াসের পরে দুইটা ওয়ার্ড কি লিখছিলেন?
Is named.
আচ্ছা, মানে এই জিনিসটা এখানে কি কারণে লিখছিলেন?
এই জিনিসটা এখানে শুনে ভুলে লিখছে, আমাদের অ্যাকশন লাইনটা এখানে শেষ হয়ে যাওয়ার কথা, এটা হওয়ার কথা একটা সেন্টেন্সের দুইটা ওয়ার্ড, তারপরে লাস্টে হওয়ার কথা এটা।
ও আচ্ছা আচ্ছা আচ্ছা।
So binding energy of nucleus divided by number of nucleons, this ratio, this much, is named binding energy per nucleon. বুঝছো?
জি স্যার।
Okay. So এরপর আমাদের যে প্রপার্টিটা আছে, binding energy per nucleon is a measure of nuclear stability. More BP means more stable nucleus. BP is also the defining factor whether nucleus will undergo fission or fusion. Fission মানে হচ্ছে breakdown, fusion মানে হচ্ছে merging. So don't mess these two words up. And it's very important not to mess up their spellings whenever you are writing question answers regarding radioactivity. This is a very important and weird type of spelling mistake that students can do to write fusion in place of fission or vice versa. Because BP is also the defining factor whether a nucleus will undergo fission or fusion, because the products slash outcome. Wow, I'm awesome. Because the product slash outcome nuclei of a nuclear reaction must always produce more stable nuclei. This is a very important sentence for you to understand. Any nuclear process will always produce more stable nuclei. From nuclear reaction, we can never produce more unstable nuclei. So any type of nuclear reaction that you can think about, typically there are three. We can have natural decay, which is the alpha, beta, gamma radiation. We can have artificial decay, which is the nuclear fission process, hitting by the neutron and breaking into daughter products. And the third one is the nuclear fusion, where naturally the hydrogen or the helium gases, they undergo merging. So any type of nuclear reaction will always happen to produce outcomes or output nuclei which would have higher nuclear stability compared to the reactants, which means you cannot do it the other way around. Or in other words, I can say, if a lot of things merge together to produce a lot of other things, the individual BP of each of the reactant products would be smaller than the individual BP of each of the output products. So কখনোই কোনো nuclear reaction থেকে less stable outcome হবে না. It will never happen. And take my word for it. It will never happen. Nuclear reactions will always produce more stable outcomes. Yes, Rafid, go ahead.
Sorry, I was confused here. Like in AS, we read about a strong force and a weak force. So, এটার সাথে কি somehow binding energy are related?
They are related. They are related, definitely. Because strong force and weak force are the two fundamental forces of the nature as well.
And sure, like you mentioned that like they exchange particles for the like graviton exchange for gravity. So in this case, can we say that to exchange those particles, the energy is used where like the energy is being utilized to exchange the particles which hold the quarks together or something like that?
Uh, if we if I say that to hold those quarks together, actually inside the nucleus there are a lot of interchangeable particles. For example, we can have gluons exchange. Sometimes we always have photons exchange, which is the responsible of the force is the electromagnetic force, for which photons are always exchanged. I do not exactly know how the quantum physics part of this whole aspect works, but one thing that I know for a fact, which I can share about this based upon your question, is that you have to understand that at nuclear level, at subatomic level, whenever we can have a lot of weird kind of interaction. Many of these interaction can give rise to production of antiparticles as well. So if you think that multiple sections of inside a nucleus, they are exchanging particles, some of those particles can also be antiparticles as well. They can be very short-lived, but they can exist. The reason I'm telling you this is that the form of energy that a nucleus holds within itself is comes from a lot of variation of interactions. The strong force interaction, the weak force interaction, the electrostatic repulsion forces, all of these things play a combined role within this part ultimately. But for the if you if and this whole thing, the total amount of energy that a certain nucleus holds within itself as nuclear energy, that can be summed up grossly by the mass deficit into c square expression. So the internal working for that energy to be stored within the nucleus can have a lot of different variation. Different particles can be involved, different type of forces can be involved, but the total sum of that can be expressed in terms of the mass deficit multiplied by c squared. Did I make sense anyhow?
Yes, sir. What you're referring to is যে energy is somewhat similar. It can be এটার সাথে relate করা যাচ্ছে, কিন্তু like we can't really be sure যে actually এনার্জিটার implicationটা কি inside the nuclei.
Well,
Because
there are denominations to as far as I know, that to the base of knowledge that our scientists have gone through as human species, but I did not study about that. But there
so
are a lot of different breakdowns that strong forces are responsible for this part of the energy, and weak forces are responsible in those isotopes where they play a role, and something like that. And also another thing that has come in recent researches, although this might sound a bit odd, I read it somewhere, I think a couple of months ago, is that uh, we there is a thing called dark matter, which is a celestial problem that we had come across, that the way different galaxies or different stars or celestial bodies behave, uh, their behavior,
Basically pushes everything inside,
they,
like
their, their,
opposite to dark
their
energy.
behavior or their movement or their orbits, the amount of mass that we can observe that they are surrounded by, and the prediction that we can make out of our mathematical equations that they should do, these two things don't match perfectly. I mean, their behavior propose that there is more mass around them than what we can actually measure. So that's something that we have defined as dark matter. Dark matter actually gives rise to a lot of interesting theories. Is that mass? One of the other interesting theories is that mass is such a property of objects. Is that this is a fundamental property in all dimensions, like in 1D, 2D, 3D, 4D, or other dimensions as well. So because we are three-dimensional beings, we can observe the three-dimensional spatial observation in fourth dimension, maybe, which is time. So this whole thing might as well be within a fourth dimensional object, and those fourth dimensional objects also have mass. But we, being the three-dimensional objects beings, we cannot observe that fourth dimensional thing, but we can actually sense the presence of that mass around. We can physically measure that effect, but we are unable to detect that. So that's an interesting theory, but it's not proved. It's not. When I say hypothesis, because dark matter could not be yet defined as something. That's why it's the name dark matter that stuck. So there are a lot of different very lucrative to be acceptable sort of ideas around that. And the reason I bring up the idea about dark matter is that sometimes in very recent researches, some scientists have proposed that dark matter might also be involved for the subatomic cases as well. So apart from these four fundamental forces that we know, uh, one is gravitational force, electromagnetic force, and strong force and weak force. The dark matter
ফিফথ
relevant,
ফোর্স হিসেবে আসতে পারে স্যার
there might
এটা।
as well be a fifth force involved. There might be
Yeah.
something that we might propose, but we cannot prove it yet. So
স্যার
there, so
এটা আসলে মানে অনেকগুলো কন্ট্রাডিক্টরি হাইপোথিসিস নিয়ে এখন আসলে কনফিউশন হয়ে গেছে, লাইক এটা থাকতেও পারে নাও থাকতে পারে, লাইক এরকম বিষয় হয়ে গেছে এখন, বিকজ
that,
অনেকগুলো ভালো থিওরি এইগুলোর এগেইনস্টেও আনতে পারছে মানে কিছু কিছু সায়েন্টিস্ট দেখলাম।
that's the point. I mean, our observation probability has gone to such a level that we can, when we need more information to process our observation that we have right now. But apparently, we don't have the means to gather those information right now. So our math has preceded far beyond the capability for our visual. So That's another thing. Rafid, I'm not sure if I confused you more or if I gave you some
No, sir.
what I
Like,
meant.
it made sense.
Okay. So the next thing that comes about is the products of Acha. So by the way, breaking nuclei needs energy, and when nuclei are produced, energy is released, like chemical bonds. এটা একটা খুব ইম্পর্টেন্ট ইনফরমেশন। এটা আমাদের পরে আমরা যখন নিউক্লিয়ার রিঅ্যাকশনের আউটপুট হিসাব করব, সেটা ফিশন বা ফিউশন হোক, এটা ওখানে এটা খুব কাজে দিবে। ব্রেকিং নিউক্লিয়াই needs energy, and when nuclei are produced, energy is released, like chemical bonds. So এখানে আমাদের একটা ফিগার আছে। This figure is not done to scale. This is a bit convoluted figure, but I'm gonna show you the actual shape of this figure from the net maybe, or actually I can look out in the microangle book as well. এখানেও থাকার কথা। এখানে যে রেডিয়েটিভিটি কত নম্বর পেজে আছে আল্লাহ জানে, সেটা আমি কনফারেন্স দেখি। এখানে রেডিয়েটিভিটি আছে হচ্ছে nuclear 376, 376. খুব গেল।
Sure, last chapter.
এই যে এখানে পাওয়া গেছে। ফিগারটা হচ্ছে অ্যাকচুয়ালি দেখতে এরকম। দিস ইজ দ্য প্রপার স্কেল ফিগার। এখানে আমার ফিগারটা এরকম কনভলিউটেড হওয়ার রিজনটা হচ্ছে there are a couple of points that I have labeled from which your questions show up. What the scientists have done, don't ask me how did they do it because I did not look it up, but you can look it up in Google if you're interested. They measured the binding energy of a lot of isotopes, pretty much everything that the scientists could get their hands on, and then they plotted the binding energy per nucleon. This is not binding energy altogether, because you have to understand, the bigger the number of nuclei, the bigger will be the binding energy. For example, naturally, if you think that sodium 23 has 23 nucleons, chlorine has about 39, or what do you use for chlorine's atomic mass? 37.5 now. What is chlorine's atomic mass? 35.5. Sorry. We use chlorine as
It's
atomic
like
mass for
35.
35.5 because naturally occurring chlorine has two isotopes, or 25%, 35%, is chlorine 37 and chlorine 35 respectively. So if you think that, if you think for chlorine 35 isotope, obviously speaking, there are 23 nucleons in sodium isotope and there are 35 nucleons in chlorine isotope. So if you think for the binding energy, obviously chlorine will have a bigger binding energy because it has bigger number of nucleons. But the total amount of binding energy is not the factor that defines the stability. How much energy per nucleon is available to the nucleus is what defines the stability. It's sort of like the what can I say? It's sort of like the per capita income defines the richness of a country. So something like that. So we have here on the y-axis we have the binding energy per nucleon of different nuclei, and on the x-axis we have the nucleon number. This horizontal axis can be nucleon number. This horizontal axis can also be plotted in terms of atomic number as well. Nucleon number basically means mass number. So we have a shape like this. Now the points that I have labeled specifically in this figure, in this figure, is that at the bottom we have deuterium. This is deuterium. আচ্ছা, এখানে এরা এই পয়েন্টগুলোকে লেবেল করে নাই কেন? এই পয়েন্টগুলো তো আমার লেবেল থাকার কথা। এখানে তো এই পয়েন্টগুলো লেবেল করে নাই কেন? এটা ইয়ার বইটা বের করো তো, ওইখানে মনে হয় লেবেল করা আছে। কি বলে, তোমাদের টেক্সট বইটা বের করো তো বলবান, টেক্সট বই থেকে ইয়াটা বাই করো, এই টপিকটা কোথায় আছে।
আপনি কি রেফারেন্স বই না মেইন কোর্স বুকের কথা বলতেছেন?
এই যে মেইন কোর্স বুক। এটা তো আচ্ছা এই যে পাইছি this is the figure that I was talking about. Actually, this figure is basically a small scale version for that large figure. Large figure মানে হচ্ছে এই ফিগারটার একটা large scale মানে ডিটেইল ভার্সন হচ্ছে এখানে। So এখানে অনেকগুলো ইন্ডিভিজুয়াল আইসোটোপের কথা বলছে। The reason I am picking this up, what I want you to see is that at the very bottom we have deuterium. Deuterium is the first nucleus that you can ever have, which is a sum of one proton and one neutron. Before that, you don't have any combined nucleus. The first nucleus or the very sole presence of nucleus is protium, which is one proton hydrogen. But there is no question of binding energy for that nucleus because there is only one particle. So the question of binding energy is does not even apply to that nucleus. So the first nucleus that could possibly belong in this table is the deuterium nucleus, where you have binding of one proton and one neutron, the deuterium nucleus. So that shows up over here in the very first. Then you have a spike at helium. Helium nucleus has a really high binding energy per nucleon. Then the graph drops down to lithium. So if you try to think about this nucleon number, this is nucleon number 2 mass number, that is this is 4, this is 6. So it jumps over to helium and then drops to lithium. Then from lithium it sort of has a curve like that. So এরপর আমাদের শেপটা more or less uniform. This is the reason I came কি করলাম এটা কি করলাম what do you see this? My GPU fan is not running at all. Oh, it's running. তোমরা কি এখানে এই জিনিসটা দেখতেছো?
So it just became 0 for a split second.
I think it was the sensors were asleep. I didn't know how to make this up. I'm ভুলে আমার original PDF off করে ফেলছি. Why am I such a dumb person? Okay, হ্যাঁ পাওয়া গেছে. The reason I labeled the figure in this format is because these are the 3 points that I would like you to remember. মাঝে মাঝে এগুলোর উপর বেস থেকে কোশ্চেন হয়. So the lowest point is deuterium, the first spike is helium, then the next drop is lithium, and then the curve goes up and eventually it goes down like this. This is supposed to be over here. The highest point of this entire graph is iron, which I would like you to see over here. This is the highest point, peak point of the binding energy per nucleon graph. The scientists measured that iron happens to be the highest point on this graph, highest means on the highest y-axis value. So এখান থেকে you observe that from the left side, একটু শেষ করি, শুধু হাত উঠাও, আমি তোমাকে কোশ্চেন করার জন্য ফ্লোর দিব. So hold your horses. আমাদের from left to right, if you slowly observe, from the very beginning all the way up to iron, the binding energy per neutron is slowly increasing, and from iron on the further side, the binding energy per neutron is decreasing, which means iron happens to be the most stable nucleus of all the isotopes that we human beings ever encountered, which means by any nuclear process, radioactive decay, natural radioactive decay, or fission, everything will slowly come to closer towards the iron structure. Iron structure as nucleus is the most stable structure that we could have our hands on. Now, if you think that a neutron star is supposed to be more stable, well, that's obvious. A neutron star is made up of only neutron, so it's not essentially a nucleus of a certain isotope. It's a whole thing is made up with neutrons and nothing else. So that's a different thing. These are earthly available isotopes that we humans could have our hands on, maybe artificially produced, or maybe they were naturally available, and we plotted them all together and we got this graph. This means, and also recall that I told you a bit earlier that every nuclear reaction will happen in such a way that the output products will all have to be more stable. Nuclearly, they have to be more stable, which means they have to have increased amount of binding energy per nucleon. That quantity has to be bigger in the reaction process, which means all of the particles which are on the left side, they are going to try to achieve more on the right, so that their output product would have a higher BEP. So these elements have the likelihood to undergo fusion, so they can merge together to produce something on the right side, but that will not surpass over to the iron. মানে হচ্ছে এখানকার দুইটা পার্টিকেল মার্জ করে এরকম কিছু প্রডিউস করবে না। হ্যাঁ করতে পারে, মনে করো এখানকার দুইটা পার্টিকেল মার্জ করে এরকম কোন একটা জিনিস প্রডিউস করলো, সেটা হইতে পারে, but they will never produce something on below their BEP level. So this is why the way this the graph is sometimes labeled, যে এখানে একটা গ্রাফ আছে, আমাদের নিচে একটা গ্রাফ আছে, যে সেটার এক্সপ্রেশন এখানে দিছে, যে these particles all the way up to iron are more likely to have fusion, not likely, they will undergo fusion because they will try to reach to the nuclear stability level of iron, whereas particles which are on the lower side of the iron, they are more likely to undergo fission, or they are most likely to undergo breakdown and eventually reach to the structure of iron. And also this also poses one more interesting beautiful thing, সেটা হচ্ছে যে যাদের যে সকল পার্টিকেলের for all the nuclei who have less binding energy per nucleon, they are essentially going to have less nuclear stability, which means they are going to be more likely to break off if they are radioactive. So their half-lives might as well be pretty small. For example, what you can see in this graph, uranium-238 is over here in the binding energy per nucleon graph. Where is uranium-235? I don't see uranium-235. Anyway, forget about this part. I was trying to tell you something, but I cannot actually make evidence for that. But the final point that I'm trying to mean is that particles which are on the left of the iron are more likely to have to undergo fusion, to merge together to produce a higher nuclei, and nuclei which are on the right side of the iron, they are more likely to undergo fission to break down and reach to the nuclear stability level of iron. So I'll take questions. Yeah, Shubhra bolo, কি বলছিলা?
So does that mean that মানে আয়রন বেসিক্যালি কখনো ব্রেকডাউন করে লোয়ার ফর্মে যেতে পারবে না?
Yes, iron will not undergo any nuclear process. Or in other terms, I can say that any type of nuclear processes that we human beings could possibly see, or we could observe, they would lead up to an end product of iron, because iron is the most stable nuclei. Which means another.
So মানে we cannot break down iron basically.
No,
So,
we cannot break down iron. Furthermore, it brings another interesting question, is that, well, if iron is supposed to be the most stable nuclear structure, how in the universe did the other isotopes get produced? In what process? Because fusion gives you these, fission gives you these. So what made these?
yeah, that is the point.
Are you getting my question?
Yeah, আমি এই কোশ্চেনটা আগেও কোথাও
Yes,
যেন
sir.
দেখছিলাম।
The
So
question
does that mean there are more elements there?
It doesn't have to be more elements. I mean, there are. I'm not sure if there is a defined theory for this, but there is one explanation that I have read, and that made sense to me, which that's why I believe my brain retained that information, that the only way we can explain the production of these elements is that they were produced in some sort of nuclear reaction that is neither nuclear fission, neither nuclear fusion. That is something that we human beings have not yet observed, but might predict that these particles might as well be produced at the very early stages of the universe, where the density of the material was so high that they didn't have enough time to convert back to iron. So they were so much packed that they took out that chunk and remained at that form. That's one theory. The other theory can be that this, if they are not produced in the process of at the early universe stage from the Big Bang, maybe these particles are possible to produce whenever multiple, if a black hole ever undergoes sort of an explosion. Because if you wonder that why does the black hole come in here, one of the things is that out of all the unknowns that we have in the celestial objects, one thing is the dark matter, the other thing is the black hole. So stuff that we cannot explain,
Unexplainable.
we bring up those two things, any of those two things, that because we can explain, maybe it is.
So this সব হাইপোথিসিসের মধ্যে ব্ল্যাক হোল এখন।
Nah, that's
সব
one.
astronomical conception
This is a hypothetical proposition which awaits confirmation. like I said, that because we could not observe them, so let's relate them to everything. Do you guys get my point?
So I get the second point, but can you explain the first density hypothesis again?
Early universe thing.
হ্যাঁ জি স্যার আপনি বলছিলেন like they were dense or something ওই জিনিসটা ক্যাচ করতে পারিনি
So the early universe hypothesis is that whenever the super atom, the Big Bang happened, super atom it was breaking down. I mean, it exploded, and it created space and time together. And the mass of the superatom was churning out from that body, and space was increased at a really high speed. And mass was spreading around within that space. That breakdown of the superatom might have produced these atoms at that instant. But what I mean is that one of the hypotheses, this is not proven, that all of these nuclei, which are not produced to produce by fusion, but they can only undergo fission, which means they can only undergo breakdown. So this high-end nuclei might be a product when the Big Bang happened. So all of those things, maybe all of those isotopes above iron that we have present in the universe, they are all produced within those fraction of seconds at the early universe stage. I'm telling
মানে
you
স্যার
what I
হাই
read and what I
ডেনসিটির
remember.
কারণে
I'm not being able to explain it logically. I'm telling you what I read, Rafid. So I understand your disappointment in me, but that's just the way it is.
স্যার মানে তখন যে like they were formed তারপর like they stayed like that because like মানে আপনি বলছিলেন যে they had a high density আমি ওই জিনিসটা কি বুঝি নাই
I mean, if you think that the entire universe was consolidated into a single zero volume particle, its density was infinite. Then as it started to spread out, then it started to give out those small particles. So there were very small particles produced, there were a large chunk of particles produced, particles which could come out, keeping some part of their intact proportional. For example, I mean, how can I put this? If you think for a physical explosion, this is just an example. This is not exactly what happened. I did not read about the proposition for what actually happened. If you think for the proposition for a bomb being blasted, let's say if I blast a bomb placed on the ground, close to the bomb, things would be more destroyed compared to the things on the outer periphery. So when the Big Bang happened, one of the proposition is that the particles which came out from the Big Bang early maybe were capable to hold their nuclear structure to a large chunk size, which are the bigger atoms. Particles which came out later were crushed more because of the explosion effect.
yes sir makes sense thank you
This is a hypothesis, by the way.
yes sir মানে like I get the মানে just actually মানে but it's not মানে proven but it's like a hypothesis right
It's a hypothesis that logically makes sense, but we haven't observed, recreated any of these things. So the way scientific research is done is that without physical proof or repeatable experiment, you cannot say something is true.
Sir, so it will forever remain a hypothesis because we
Unless,
can't recreate the Big Bang.
well, whether we will be able to recreate the Big Bang or not, that's actually another big celestial question. I mean, the speed at
স্যার
which
অনেকে ভাবে যে হ্যাড্রন কলাইড পার্টিকেল দিয়ে কোলাইডারটা দিয়ে হচ্ছে মানে পসিবল বলে ওই টাইপের ওই লেভেলের আর কি ইফ ইট ইজ অন আ লার্জ স্কেল যদি কনস্ট্রাক্ট করতে পারে তাহলে পসিবল প্রবলেম
that is actually, I mean, what can I say? I mean, you see, there are myths and there are myth bustings. Hadron Collider works with subatomic particles pushed towards each other at a very high speed. They can create fraction of particles to study them. To be able to create a black hole, the amount of mass that you need to accelerate at that amount of speed is not possible for the capacity of Hadron Collider, which have been proved over time and time. So I don't think Hadron Collider pose any logical problem to our existence. However, ITER can. ITER is the project. তোমার question আমি আসতেছি. ITER is the project which is trying to recreate cold fusion. So cold fusion kora is a difficult thing to achieve, to be honest, because the reaction can be started, but it cannot be controlled or sustained in a human-made environment like all the stars. In the stars, the gravitational force work as control, but we cannot work with that much mass for a battery. So we have to have some other form of control, and having that force, that control to that precision level is actually quite troublesome. We could not yet crack it, simply put. প্রত্যেক যে কোশ্চেনটা করছো সেটা হচ্ছে যে because we cannot recreate the Big Bang. One question that lies with this thing is that we have seen the universe is expanding. Now, there are 3 possible outcomes for what could possibly happen to the universe. Scientists have calculated that there is a certain value for critical mass, that if the mass of the universe is this much, and I mean, as the universe is spreading out, as the distance between the stars are becoming, galaxies are becoming bigger, their gravitational force is becoming weaker. So one possible thing is that it will be an ever-expanding universe where that reduction of force will ever keep on happening, and the distance will ever keep on increasing. That's one possible outcome for the universe. The other possible outcome is that it will be, if we have the exact value of the critical mass for that the scientists have calculated for the universe, that there would come a point where the universe will expand and the rate of expansion will slow down, and eventually it will come to I mean, as the universe will expand more and more and more, its expansion rate will become less and less and less, and eventually there will come a certain point that this rate will become asymptote, which means the universe will almost get a perfect shape or uniform density. It will attempt to increase, but it wouldn't be able to increase. I mean, it would have enough inertia to go outwards, but it would also have enough gravitational pull not to make it come backwards. That's the case for critical scenario. And if the universe's mass is actually bigger than the critical mass, then we'll also have super crunch, which means the universe is expanding. At one point, the gravitational force will start to pull back everything. If that is possible, and if human civilization actually sustained till that point of time, I don't know, that's a huge amount of time that we're talking about, this is just all predictions, then we might be able to see the super crunch, provided that we are alive and we are still able to observe
আমাদের
it from a point
সিভিলাইজেশনই ওই
of-
পর্যন্ত এক্সিস্ট করবে না।
Shubho, it's important that you let me finish. I really appreciate that. So if that happens, if we can, as a human species, if we can observe the super crunch, maybe it would be possible for us to see that, but it all lies in a super far away future. So the question that you asked, that we can never recreate the Big Bang, we don't know that for sure yet. তুমি বুঝছো কি বলছে?
Yes, sir. Which?
So if I go back to the basic stuff that we have to deal with for our exam, here's the thing, and then we are gonna get over here. We have some mathematical calculations coming up. We have some symbols that we have to work with. U is the symbol of atomic mass unit. 1U is 1/12 of mass of 1 carbon-12 atom. This is very important. Atom with star marked, because the carbon-12 nucleus's mass would be 12U minus the 12 mass of electron. This is the mass of carbon-12 nucleus, and U is 1/12 of the mass of 1 carbon-12 atom. So 12U is the mass of 1 carbon-12 atom. এখান থেকে যদি আমরা 12টা ইলেকট্রনের মাসকে সাবট্রাক্ট করে দেই, তাহলে আমরা একটা কার্বন-12 অ্যাটমের নিউক্লিয়াসের মাস পাবো। সো বাই ডেফিনিশন দিস ইজ অ্যাটম, সো ডোন্ট মেস দিস আপ। এটা কোনো সময় হয় ডেফিনিশনে আসে। এই ইউ এর ভ্যালু তোমাদের দেওয়া থাকবে, which is 1.66 × -19 kg -27 kg। এটা তোমাদের ভ্যালু দেওয়া থাকবে, you don't have to memorize this, ফর্মুলা সেটা থাকবে। এখানে একটা ক্যালকুলেশন দেখাচ্ছি আমরা, যে ক্যালকুলেশনটা আমাদের ফার্দার ডাউন দ্য লাইন অনেক কাজে দিবে। energy calculation. 1U mass, if exactly 1U mass is converted to energy, then how much energy are we gonna get? So we can calculate this up. E equals to 1U c into c square. So 1/16 to the minus 27 kg into 3 10 to the 8 meter per second squared, which gives us about 1.49 to the minus 16 joule. Now we're trying to convert this energy into electron volt. 1 electron volt is this much joule. So 1U would be equivalent to this much electron volt of energy. I've written 1U equals to because we are essentially now converting to talking about mass converted to energy. So you have used mass on the left side, we have written energy on the right side. This equation is currently valid because we are talking about this conversion. Another thing that I'd like to tell you is that in a Newtonian scenario or macro case of world, not essentially macro case of world, I mean for our regular experiences, mass and energy can be considered to be a conserved quantity, and that works perfectly. But whenever we go for super massive cases, not essentially super massive cases, forget about super massive cases, let's not get there. For subatomic cases, for nuclear cases, mass and energy are interconvertible in it. So this is the reason that in nuclear physics, we do not essentially use, in most cases, we don't use the exclusive term mass, or we don't use the term exclusively energy. Rather, we use a specific term that's called mass energy, mass dash energy. That's a new quantity that is defined for the nuclear physics or the quantum physics scenario, which means that this is the amount of thing that we're talking about. I mean, if this amount of thing is available in energy form, we're gonna get this much energy. If this much of energy is available in the mass form, we're gonna be talking about this amount of mass. So we're gonna see about this quantity and some of its implication after a while. I'm just telling you that this is gonna show up in our calculation after a while. Hold up a bit. I'll give you time after a while. Ekটু wait koro. So one U amount of mass can give us this much amount of electron volt, which gives about 933 to 10 to the power 6 electron volt, or 933 mega electron volts, from which we can get this equation. If you can remember this 933 number, it can prove to be helpful for you for a lot of calculation. If you can't remember this thing, you can always find out this calculation by putting these numbers in a calculator. So I'm not asking you to memorize this, but if you can remember this thing, you might have some advantage later on. You might. So 1U amount of mass can be considered to be equivalent to this amount of energy. That's why I use the both-sided arrow, which is exactly equal to 933 mega electron volt. And then we're gonna see some nuclear equation and its decay processes. But I'll take question. Mugdho, yes.
স্যার উপরে যে নিউক্লিয়ার ম্যাস ইকুয়েশন দিয়েছিলেন ওখানে লেখা ছিল 12 me but carbon has 6 electrons, so shouldn't it be 6 me?
আচ্ছা হ্যাঁ, sorry, আমি ভুল বলছি. Thank you. I'm gonna correct this right now. Thank you. I have saved it, so it's gonna be like this. It is supposed to be 6. Is that it? I guess so.
Yes sir.
Sure. So if we have a look at some nuclear equation, we know the alpha decay. Alpha decay is just alpha decay. Beta minus decay is beta minus decay. Beta plus decay is beta plus decay. You know these stuffs. Beta plus decay আমাদের output হচ্ছে positron. That is the antiparticle of electron. এগুলো আমরা AS level এ পড়ছি in detail, so you might as well remember them. And then we have the quark structure. Proton quark structure হচ্ছে up up down. Neutron হচ্ছে up down down. Beta minus decay practically one down quark pegs into one up quark, and an electron is released. And in beta plus decay, one up quark breaks down into a down quark, and then positron is released. Or in other terms, you can say one electron is absorbed. That's also one way to express that. Then comes the radioactivity. Radioactivity is a spontaneous random process. Spontaneous means the speed spontaneous means it means the rate of decay cannot be the speed of the process, that is rate of the decay, cannot be affected, altered, changed by changing variables like pressure, temperature, light, intensity, or any other physical variable. These things cannot affect the rate of natural decay. That's what it means meant by spontaneous. and then randomness has 3 aspects. এই 3টা aspect নিয়ে আমাদের কোশ্চেন হয়, এই aspect গুলো খেয়াল করো। It number 1 and 2 can be a bit confusing. 3 is actually pretty simple. আমি 3 নাম্বারটা আগে বলতেছি। The ionizing radiations from reactive decay can happen at any direction from the nucleus, which is obvious. So if you have a lump of reactive nuclei and it's giving out ionizing radiation, exactly in which direction the ionizing radiation is going to come out, you cannot predict that from earlier. It could happen in any direction around that block. Number 1 টা খেয়াল করো। Number 1 says at any point of time, we cannot exactly predict how many nuclei will break or exactly which nuclei will break. So let me tell you what it means. Let's say you have a radioactive isotope lump of, let's say, 1000 atoms. You have 1000 undecayed nuclei. Let's say the half-life of this specimen is 10 minutes. So you would expect that after 10 minutes, the number of remaining nuclei would be 50. But in two cases, it might not be exactly 50. It may be 49, it can be 52, it can be 48. It can be somewhat different from that. Radioactivity being random means that we can never predict exactly how many nuclei will break down within a specific duration of time. We can guess around. We can have a prediction that is pretty close, but we cannot exactly guess that exactly how many particles will break down within a certain duration of time. We can calculate a number that is pretty close to that possibility, but perfectly guessing that number is not possible. And also, we cannot exactly pinpoint which of these atoms are going to break down in the next 1 or 2 minutes. We cannot do that. So if you have 1000 particles to start with, you know that after 10 minutes, if 10 minutes is the half-life, you know that 500 particles will be remaining. So exactly which 500 would decay, you cannot pinpoint them from earlier. Any 500 might decay. So these are the 2 aspects that at any point of time, you cannot exactly predict how many nuclei will break or exactly which nuclei will break. This is the first aspect. Second aspect is that when or after how long any specific nuclei will break cannot be predicted either. The মানে হচ্ছে, if you pinpoint one single nuclei within a radioactive specimen and you predict that this nuclei is going to break down exactly 2.3 minutes, you cannot do that. Exactly when a certain radioactive nuclei will break down, we cannot predict that either. Precisely, we cannot predict that. So a nuclei might break down right after a fraction of a second, or it might take billions of years to break down. So which exactly after how much time one radioactive decay will happen from a specific nuclei cannot be predicted. So number 1 and 2 difference টা বুঝো। Number 1 difference হচ্ছে number of decay over a fixed duration of time cannot be predicted, or exactly which nuclei will be decay, that cannot be predicted from earlier. Whereas number 2 says for exactly one specific nuclei, unstable nuclei, will break when or after how long time will the breakdown of one specific nuclei will happen, that cannot be predicted from earlier as well. So these two are a bit different. One applies for total number of decay over a duration of time. The other one works with the required amount of time for exactly, precisely, or predefined one atom or one nucleus to break down. So they are a bit different, so don't mess this up. We don't have anything else over here, so the calculation part is not in this lecture. I'll look up for more. I might have more. If I don't have, then we'll pick this up from the book as well. No problem. These are same stuff from another student, I believe. আচ্ছা, এখানে A2 রেডিয়েটিভিটি নিয়ে আর কিছু নাই। আচ্ছা, ক্যালকুলেশনের পার্টে আমাদের কিছু পরে ক্যালকুলেশন আছে, আমি ক্যালকুলেশনের পার্টে একটু পরে দেখাচ্ছি। I'll take a bit like washing. So
স্যার একটা কনফিউশন ছিল
বলো।
স্যার ওই যে আপনি তখন যে লাইক অ্যাটমিক মাস ইউনিটের যে এনার্জি ইকুইভ্যালেন্সিটা দেখালেন সো দেয়ার উই কনসিডার দ্য ভেলোসিটি টু বি দ্য লাইট স্পিড তো ডাজ দ্যাট মিন যে লাইক এটাকে আমরা জাস্ট ধরে নিচ্ছি যে ও যদি লাইট স্পিডে থাকে দেন কত এনার্জি ইকুইভ্যালেন্ট হবে নাকি হচ্ছে
No,
like inside the nucleus it moves in that
no.
speed?
Inside the nucleus, the mass would remain as the energy. That value can be calculated using the constant of light speed. I mean, for that conversion to happen, it doesn't have to move at light speed. I mean, the speed of light in empty space is a natural constant, like Planck's constant or Avogadro's constant. So it doesn't have to be moving at that speed to express itself as energy. That energy is within that nucleus if that nucleus is apparently perfectly stationary. And C is actually a calculation constant, not essentially a physical required constant.
Yes, sir, বুঝছি।
That makes better sense. কি যেন দেখতেছিলাম, আচ্ছা এখানে আচ্ছা এটা থেকে ট্রাই করলে মনে হয় পারা যাবে। এখানে আমাদের ক্যালকুলেশনের ভালো কিছু এক্সাম্পল আছে। So we're gonna use this book for the later part of the discussion. So we have example for nuclear fusion over here, where 2 deuterium is converting into helium-3 and producing 1 neutron in energy. And then we have fission. This is just example. This is the case for, this is uncontrolled or accelerating chain reaction, and this is the control chain reaction which happens in the reactor. This happens in the bomb. And then the idea of random decay is given. One of the expression for the random decay for reactive process is given by the zigzag part of a graph. We usually don't ever get a smooth line like this out of an actual experiment. Actual experiment will always give us graphs which have some sort of zigzags on top of it. So that's that. And these are the equations that we have seen. Where is the energy calculation? বই শেষ? আয় হায়, I need to have some energy calculation. Energy calculation কোথায়? আচ্ছা, binding energy, mass energy equivalence, we have more binding energy, nuclear equations, stability of a nuclei. তো বিপদে পড়া গেল। আচ্ছা, এখানে এক্সাম্পল গুলো আমরা একটু দেখি, সমস্যা নাই। I'll pick up questions from the worksheet and I'll discuss questions from there to make sense of how to calculate the energy output of a nuclear reaction. এই জিনিসটা খেয়াল করো। Let's say this question says that the mass defect and the nuclear binding energy. So we have talked about the mass defect or mass deficit. They are showing this thing over here, and then we have a calculation over here. Calculate the mass defect for a carbon-14 nucleus. Now you can see over here, these are the questions where the value of multiple numerical numbers are given to a very large number of decimal places, because other than this amount of precision you cannot get answers which will be of any meaning. So the measured mass of a carbon-14 nucleus is given by this amount, and the nucleus contains 6 protons and 6 neutrons, which if we calculate individually gives us a total mass of this much. These numbers would be given to you in your question, because your actual formula sheet will never have this many decimal places. In the formula sheet, if you turn over, you will find out. Let me just show you. Why not? Formula sheet কোথায়? You have 41, maybe 40, 41. So we have a look at the formula sheet. In the formula sheet, you are gonna get the rest mass of electron and rest mass of proton in kgs, and you have the value of U given. So you don't have the values for in terms of in terms of U, how many is that? You don't have those values, because if required for the question to work with those numbers, this I mean, these numbers would be already given to you, so you don't have to bother about that. So we can calculate the individual sum of the masses is given by this number. The mass defect is this much. So if we do the subtraction, we get this amount of mass defect. So that's basically it. Then the question says that calculate the mass defect for nitrogen nucleus. The measured mass is this much. So you can do the subtraction and calculate this out. Then they are showing us the mass energy equivalence, which we talked about. Binding energies over here. The question says calculate the binding energy in megaelectron volt of a carbon-14 nucleus with a mass defect of this much. Okay, binding energy in megaelectron volt. আচ্ছা এটা তো খুব কঠিন কিছু না। 1U equals to 931 megaelectron volts. So at equal to atomic electrons. আচ্ছা এখানে তো কিছু দেখাই নেই। Stability of a nucleus how you আচ্ছা ওয়ার্কশিটে কোশ্চেন বের করি, নাহলে এটা পাওয়া যাচ্ছে না। তোমাদের মেইন বইটা থেকে এটা এই রিলেটেড কোনো কোশ্চেন আছে? Binding energy for nucleus step 3 binding energy per nucleon divide করছে। আচ্ছা এটা তো নরমাল জিনিস, এখানে ঝামেলা নাই। The mathematics of radiative decay. So this is these Becquerels and everything, count rate, okay. Decay graphs and equations, okay. Half-life. Nope. আচ্ছা এই যে কোশ্চেন নাম্বার 6টা আমরা ট্রাই করি। এই কোশ্চেনটা দেখো, this is a nice question. Let me copy this up from here. I cannot deselect this. Okay. বলবো না, আমি এই কোশ্চেনটা একটু তোমাদের করে দেখাই। Number 6. This is a type of question that usually is, in my opinion, the most challenging type of questions from this chapter, where you have to use some ideas to be successful. দেখো কোশ্চেনটা পড়া যাচ্ছে এভরিওয়ান? আই কনফার্ম করো, নাহলে আমি আরো বেটার বড় রেজুলেশনে কপি করতে হবে। পড়তে পারতেছো?
Yes, sir.
Actually, maybe if I try and get this at a bit higher resolution, not that high, maybe 350, 200 হলে এইটুক। Let's copy this one, 200. বড় করলে ফেটে যায়। আচ্ছা এখান থেকে দেখো, যতটুকু দেখা যাচ্ছে ততটুকুই বড়। I think this is readable. সবাই পড়তে পারতেছো?
জি স্যার।
খেয়াল করো, the fusion reaction which holds most promise for generation of electricity is the fusion of tritium 3H1 and deuterium 2H1. The equation below shows the process. So we are merging hydrogen, tritium with deuterium, and we are producing one helium atom, helium-4, and one hydrogen gas, protium is released. Number 8 was calculate the change in mass in this reaction. Beta was the binding energy, the energy released in the reaction, and Sita was the energy released if 1 mole of deuterium were reacted with 1 mole of tritium. আমরা একটু বুঝি চেঞ্জ ইন ম্যাস ইন দিস রিঅ্যাকশন, এটার মানে হচ্ছে how much is the difference of the masses on the left side and on the right side. So that is not very difficult to do. Chat window থেকে লিখছে। Oh, Mashavi, thank you. But I really need to show this. Maybe after this one. So let's calculate the total mass of the reactant. So let's say this is the solution for A. So total mass of reactants equals to হচ্ছে 3 point আচ্ছা আমি একবার লিখলে কাজ হইতো, আমি এভাবে না লিখে একবারে লিখি, কাজ কমাই। The change in mass হবে হচ্ছে delta m equals to total mass of the reactants minus delta m total mass of the reactant এর ডান পাশে গুলো কি বলে জানো? প্রোডাক্ট না?
জি স্যার, প্রোডাক্টই বলে।
So এখানে তো changing mass বলছে, so it would have been better if I did the other way around, প্রোডাক্ট আগে লিখে reactant পরে লিখলে ভালো হতো। But I might as well give a modular sign over here because I'm trying to find out how much change is happening. I should do that actually. Forget about the modular sign for the time being. Modular signটা আমাদের বিপদে পড়লে আমি দিব, but আশা করি বিপদে পড়া লাগবে না। Change always means final minus initial, so might as well stick to the principle. That's why I rewrote this equation. So এটা করলে এখানে আসবে হচ্ছে আমাদের প্রোডাক্ট আছে হচ্ছে হিলিয়াম আর হাইড্রোজেন। হিলিয়ামের মাস হচ্ছে এইটা, হাইড্রোজেনের মাস হচ্ছে হিলিয়ামের মাস হচ্ছে এটা, হাইড্রোজেনের মাস হচ্ছে এইটা, আর এই দুটো হচ্ছে এদিকে। সো টোটাল জিনিসটা অ্যাড করে সাবট্রাক্ট করে দেখো কত আসে। 4.001506 প্লাস 1.007276। আজকে আবিয়াস ক্লাস করতেছে না?
না মনে হয় স্যার।
হ্যাঁ স্যার, রোল 9।
এটা হিসাব করে দেখো কত হয়। I'll also do in my calculator. So and use all the decimal places.
স্যার ব্র্যাকেটের বাইরে ওটা কি লিখেছেন? ইউ?
হ্যাঁ, 1506 plus
মাইনাস এসে তো স্যার, মাইনাস 0.
minus 0.02
71
0.02 u। আচ্ছা, এটা হচ্ছে আমাদের mass deficit, changing mass of the reaction. আচ্ছা, if you wondered that how is it possible that the mass change could be negative, well, it is possible in nuclear reactions, because what I want you to understand that within this thing we have mass plus energy, within this thing we have mass plus energy, within this thing we have mass plus energy, within this thing we have mass plus energy. So we have when the reaction happened, the answer being negative essentially means that the products have a slightly bigger mass compared to the reactants, which means energy from the products could be converted into mass over here. That is possible, and I'll look out for the answer. Did they give the answer in negative or not? এটা হচ্ছে কোন ইয়ার? এটা হচ্ছে চ্যাপ্টার 31। চ্যাপ্টার আনসার কি এখানে দেওয়া আছে নাকি পরে দেওয়া আছে? answers glossary index acknowledgements CD-ROM. Yay! Answer to the end of chapter questions. Wait. এটা কি আমরা কি করতেছিলাম? এত ভেজাল। এটা কি সেলফ অ্যাসিস্ট্যান্ট এন্ড অফ চ্যাপ্টার কোশ্চেন নাম্বার 6 এন্ড অফ চ্যাপ্টার কোশ্চেন। এটা কত নম্বর চ্যাপ্টার? চ্যাপ্টার 31 এর কোশ্চেন নাম্বার 6। ডিক্রিজ ইন মাস ইকুয়ালস টু এত। আচ্ছা, যেটাকে আবার তারা কেজিতে কনভার্ট করছে হচ্ছে এটা দিয়ে মাল্টিপ্লাই করে কেজিতে কনভার্ট করছে। এরপর বলছে হচ্ছে রিলিজ এনার্জি হচ্ছে এই ডিক্রিজিং মাসকে ওহো আমি তো ভুল করছি, সরি ভুল করি নাই, লিখছি ঠিক, বলছি ভুল। বলবান দেখো, whenever the reaction is happening the change in mass is becoming negative, which means what? This is less massive, this is more massive, ঠিক না everyone?
জি স্যার।
এই দুটোর মধ্যে বড় মাস কোনটা? রিঅ্যাক্টরের মাস বড়, প্রোডাক্টের মাস ছোট, which means in this process some mass got 9, some mass got gaib. So we can calculate how much in a mass was lost from this process and convert that energy in half mc squared. So that's essentially what they did. So they multiplied that amount of energy, এই যে এখানে কই গেল নাম্বার 6, এই যে এখানে we have that amount of energy over here, kg. So we have this calculated in U first, and then we convert this into kg, then we got convert that kg into half mc square formula, half না সরি ভুল বলছি, and then it says that how much, so এটুকু হচ্ছে আমাদের একটা রিঅ্যাকশন থেকে কতটুকু এনার্জি বের হবে একটা রিঅ্যাকশন থেকে। এরপর সি নাম্বার কোশ্চেনে বলছিল হচ্ছে যে কোশ্চেন নাম্বার সি তে বলছে the energy released if 1 mole of deuterium are reacted with 1 mole of tritium, which means you are gonna have Avogadro number of tritium plus reacted with Avogadro number of deuterium. So basically এই রিঅ্যাকশনটাই Avogadro নাম্বার যত বড় তত টাইমস হবে, because we are working with 1 mole. So that would mean that we need to multiply that amount of energy with the Avogadro constant. তাই কি করছে না? হ্যাঁ, exactly. So that whole amount of energy multiplied by this much is giving us this much energy. Now, why is this promising? The reason I would like to discuss this, that the reason this reaction is promising is that 1 mole of tritium, hydrogen tritium, would have a mass of about 3 gram, about. So, and 1 mole of deuterium would have a mass of about 2 gram. So which means if you could somehow make the fusion reaction altogether completed between 1 mole of tritium and 1 mole of deuterium, so that is about 5 gram of gas, you could get about nearly 1.8 into 10 to the power 12 joule. 1.8 into 10 to the 12 মানে অনেক জুল। 10 to the power 9 হচ্ছে গিগা, তারপরে হচ্ছে tera. So that is about 1.8 terajoule. So that's a huge amount of energy from a very small amount of mass. But achieving this is actually quite challenging. Okay, this was a good question. এই পিডিএফটা অনেক ভালো, এখানে সব আনসার টানসার দেওয়া আছে এবং অঙ্কগুলো মোটামুটি করে দেওয়া আছে, so that helps a lot.
স্যার এটা তো আমাদের কোর্স বুকটা না?
অ্যাড করে করছো
Listen.
কইছিলাম কোন চ্যাপ্টার ছিল এই চ্যাপ্টার ছিলাম আচ্ছা আরেকটা কোশ্চেন দেখি মানে এখান থেকে উপর দিয়ে গেলে সুবিধা হবে এক্স্যাক্ট সো এটা একটা জিনিস proportions বাইন্ডিং এনার্জি ক্যালকুলেশন কোথায় তো মহা প্রবলেমে পড়া গেল তো মানে আমাকে একটু সময় দাও আমি বাইন্ডিং এনার্জি ক্যালকুলেশন একটা দেখাতে যাচ্ছি তোমাদেরকে বাইন্ডিং এনার্জি ক্যালকুলেশন না দেখাইলে শান্তি হবে না হুম আচ্ছা এই যে পাওয়া গেছে একটা Figure 8 shows the variation with the nucleon number of the binding energy per nucleon of a nucleus. So binding energy per nucleon on the y-axis, on the axis we have nucleon number. On figure 8 mark with the latest position for the nucleus with the greatest stability. So you pick a dot দিয়ে এখানে s দেখাইতে হবে, which is iron, but they ask for s, so you label it s. One possible fission reaction is this one. So uranium-235 reacting with 1 neutron, you get barium, krypton, and 2 free neutrons. On figure 8.1, mark the possible position for the uranium, krypton, and so uranium has to be labeled pretty far on the far right. Krypton have to be labeled on the slightly left over here. Anywhere is possible, but uranium should be on the more right side. Krypton should be a bit on the left side, but definitely not left of the peak because krypton is on this over here, somewhere over here. Then it says the binding energy per nucleon for each of the nucleus is as follows. So uranium-235 is binding energy per nucleon, barium per nucleon, krypton per nucleon. Use this data to calculate the energy released in this fission reaction, giving answer to 3 significant figures. Now, here's the deal. In this process, we're going to have some energy released. So what we can do and what we is that we can calculate the total amount of energy that was involved, that was incorporated in this thing. So binding energy per nucleon for uranium-235 is this much. Okay, binding energy for uranium-235 is this much. So the reaction was that we had, I'm just reaction to roughly like this, see, uranium plus 1 neutron produced gave us the barium plus krypton plus 2 neutron. This was the core equation that we are given. So এখান থেকে আমরা হিসাব করতে পারবো হচ্ছে what is the total binding energy of the nuclear reactant side. Neutron is a free neutron, so এটা কোনো binding energy নাই. So binding energy of the reactant side equals to হচ্ছে 235 multiplied by 1.2191 into 10 to the power minus 12 joule. This is the total amount of binding energy stored within the uranium nucleus. And then the total amount of binding energy of the products would be the relevant multiplication and sum of these things. So this can be written as 144 into 1.3341 into 10 to the power minus 12 plus 90 into 1.3864 into 10 to the power minus 12. So এই ভ্যালুগুলো কত কত আসে একটু বলো। Give the numbers up to 4 decimal places. Or maybe exactly as you see on the calculator, that's even better. This is coming
This is
2.64885 minus 10 জুল, আর এটা আসে হচ্ছে
sorry 3.16296 in 10 power minus 10.
168864
So 3.16296 instead.
কি বলো?
That's right. I'm sorry. I'm gonna have a 3341 to late.
334 লেখো নাই?
So 3.168864.
হ্যাঁ 3.168864 minus 12 জুল। আচ্ছা, এখানে খেয়াল করো আমাদের টোটাল বাইন্ডিং এনার্জি বেশি আসছে কোথায়? রিঅ্যাক্ট্যান্ট সাইডে। বাইন্ডিং এনার্জি বেশি আসার মানে হচ্ছে যে in this process the reactants would have a bigger amount of binding energy compared to the reactant side. Now the process whenever we have binding energy involved, not the masses by which we can calculate the energy released from these two reactions, is that we can do a subtraction of those two things and that will give us the total energy output of this reaction. So if we do the subtraction of these two numbers,
So it's gonna be 10 to the power minus 10 right hand side of that.
oh sorry I'm ভুলে টুল দিয়েছি, my bad thank you. সেটা সাবট্রাক্ট করলে কত হয় দেখো তো? 3.168864 minus 2.864885 into 10 to the power minus 10. So this gives me 3.03979 10 to the power minus 11 joule. আমাকে আনসারটা কততে দিতে বলছিল? Then using this fission reaction give answer to 3 significant figures. 3 significant figures এর আসবে হচ্ছে 3.04. I hope it worked out. Let's look at the mark scheme. This is number 2. Yeah, 3.04. ঠিক আছে। And then it says the equals to mc square করতে বলছে, equal to mc square করার জন্য জাস্ট এনার্জিটাকে c square দিয়ে ভাগ করে দিলে তোমার mass equivalent চলে আসবে। This was not that challenging. There is a question which actually I cannot do and I struggle and stutter and move back and forth for that question every year. এই কোশ্চেনটা somehow আমার এখনো পুরোপুরি আয়ত্ত হয় নাই, that's the whole thing, that's the point that I'm trying to tell you. Maybe this one. আচ্ছা, we'll pick up more questions from this worksheet next class. আজকে একটু বন্ধ থাক, ঠিক আছে? আর তোমাদের রবিবার, সোমবার এবং আজকের মানে গত বৃহস্পতিবার, রবিবার এবং আজকের 3টা লেকচারই আমি একটু করে আপলোড করে দিচ্ছি। আগে দুটো আপলোড করতেছি, তারপর এটা আপলোড করবো। ডোন্ট ওয়ারি। থ্যাংক ইউ ভেরি মাচ। গুড নাইট কিডস।
স্যার
বলো।
স্যার আমার একটা কোয়েশ্চেন ছিল, এটা রিলেটেড না, অনেক আগে কোয়েশ্চেন।
বলো।
তো সার্কুলার মোশন নিয়ে।
বলো, সমস্যা নাই।
স্যার রেডিয়াস বাড়লে টাইম কি কমবে?
কি বাড়লে?
রেডিয়াস বাড়লে।
তোমার ইকুয়েশন কি?
আমি ওই ইকুয়েশনটা বের করার চেষ্টা করতেছি বেসিক্যালি।
তুমি এই যে ওয়ার্কিং টুকু করছো, ওয়ার্কিং টুকু ছবি তুলে গ্রুপে দাও, আমি ওখানে আলাপ করছি, ডোন্ট ওয়ারি, আই উইল রেসপন্ড।